Okay, in this presentation we're going to look at the gamma distribution. The repair time in hours for an industrial process, an industrial machine rather, has a gamma distribution with a mean of 1.5 and a variance of 0.75. Okay, so those are the two key values we're going to be working with. It's always a good idea to actually state what the x is going forward when we talk about some random variable x or w or whatever. So just actually, it's the repair time in hours. Just actually state that this is the variable and it has a connection to some symbol like x. Determine the probability that the repair time exceeds 2 hours, and determine the probability that the repair time is at least 5 hours given that it already exceeds 2 hours. Okay, so that's the sort of conditional probability that we will be working with. And it uses, part B uses the answer from part A. Okay, so we can sort of turn to the lecture notes here. So this is sort of generic text that we would use anytime we sort of want to read up about the gamma distribution. Here, a random variable wn follows a gamma distribution with a shape parameter n and a rate parameter lambda. Okay, just as a sort of quick remark, it's common to actually sort of state them in terms of alpha and beta, and we will actually shortly down below when we look at the next part. But here, the notation is denominated in terms of n and lambda. Now, this is the key one here. The survival function, which we're going to use later on, this is the cumulative distribution function, which is essentially the complement of the survival function. And down here we have the density function, which we're not really going to use in this instance. Just as a sort of quick remark, when we're using this formulation that we have here in terms of n and lambda, it presupposes that n is an integer, okay? And that means that simplifies the mathematics that is associated with the cumulative the gamma distribution for all these formulas massively. Essentially, we can write them in terms of these sort of discrete summations, okay? Conventionally, alpha and beta are any real numbers, so that's why there's a bit of a mismatch there, because we're sort of dealing with a special case of the gamma distribution where the shape parameter is specifically an integer, okay, in this particular set of videos, just for the sake of tractability, essentially. That's it, really. We'll move on to the method of moments. So to tackle this problem, we're going to use the method of moments for the gamma distribution. So the shape parameter here, now I'm denoting it as alpha because this is coming from a textbook as well, and that is the expected value of x squared divided by the variance of x. The rate parameter beta is the expected value of x divided by the variance of x. Okay. Now again, we're using the notation n and lambda later on. So using the method moments for the shape parameter n equals the mean squared, which is 1.5 squared divided by the variance. 1.5 squared is 2.25, divide that by 0.75, which is the variance, and we get 3. And again, n is an integer, 3, okay? The rate parameter lambda, also known as beta in other cases, is the expected value divided by the variance, 1.5 divided by 0.75, and in this case it's 2. So gamma distribution with rate parameter 3, shape parameter 3 and rate parameter equals 2, straightforward enough. So we can use our expression here now. This is the cumulative, the survival function, which we're given in the notes. Okay, we have n is 3, so the summation, the upper index of the summation is n minus 1, which in this case is 2. Actually, I'll just go back there a little bit. Up here. So this particular formula here, n minus 1, so that's 3 minus 1. Okay, that's the upper summation, upper limit of the summation. So k equals 0 to 2, and we have e to the minus lambda t times lambda t to the power of k divided by k factorial. So that's where we'll use our value of 2, lambda equal 2. So we piece it all together there. We just go for each of these terms, k equals 0, k equals 1, and k equals 2. Just evaluate them out, and then we just add them all up. Lambda is 2, so e to the minus lambda t is e to the minus 2t, and that's common to each of the expressions. 2t to the power of k divided by k factorial. Well, k is equal to 1, that's just equal to 2t, and when k is equal to 2, that is 4t squared divided by 2. So Overall, this is the overall expression that we're going to be working with. E to the minus 2t times 1 plus 2t plus 2t squared. Okay? So, denoting the lifetime as a variable x, so the probability of x is greater than 2. Essentially, we put in our value of 2, e to the minus 2 times 2, which is e to the minus 4, actually, it's minus 4. 1 plus 2 times 2 plus 2 times 4, that's 13, okay? And that's, 13 to the power of e minus 4, little typo there. What we're also interested in is the probability of x greater than or equal to 5, so e to the minus 2 times 5 times 1 plus 2 times 5 plus 2 times 25. So that's 61 to the power of e minus 10, okay? So we're going to use that shortly. So that's the first answer there. Part A is 13 to the power 13 times e to the minus 4. You can evaluate that if you want. I just left it there as is. I could have probably worked it out, but you should be able to work that out. And the conditional probability of x being greater than 5, given that x is greater than 2, that is 61 divided by 13 times e to the minus 6. That's e to the minus 10 divided by e to the minus 4 is e to the minus 6. Just in case you're wondering. And that works out to be 0.01163. Okay, so that's it there.